that, I'm going to present a solution that we propose for performing intelligent routing based on reinforcement learning. This solution was recently published in the international journal Transactions on Network and Service Management. And after that, I'm going to present some conclusions and some future work related with the use of reinforcement learning in diverse areas. Okay. Then the idea is to present the networking routing problem. Networking or the routing is a fundamental problem in the networking area. Basically, this task is to select a path for packet transmission, and selecting this path involves diverse criteria like cost minimization, maximization of utilization, quality of service provisioning, and the problem here is very easy to explain that how to perform this selection in an efficient way. Okay. Then, in order to perform or in order to address this problem, in order to deal with this problem, we have two approaches: static and dynamic routing. Obviously, static routing is when used for computer networks not very large, and when it's possible to perform configurations in a manually way. Okay. And dynamic routing is used for large networks, and this is the topic that we are going to talk in the rest of this presentation. Okay. For performing dynamic routing, we have two approaches: the distance vector protocols and the link state protocols. Okay. Then I'm going to discuss briefly these kind of protocols in order to understanding better the problem that we are going to resolve by using reinforcement learning. Then the distance vectors determine the best route for data packets based on distance. In this case, the distance is the quantity of hops that are needed to perform in order to reach a destination. That's basically the main idea of the distance vector routing protocols. In this case, the mainly weaknesses of this kind of solutions or solutions based on distance vectors protocols is that the routing information is not covered by the router itself. We need to distribute the routing information. Then we can work with non-updated information. There is delay in the delivery of the routing information. As we need to distribute the information, we can cause network overhead. And the most important example of distance vector protocols is the routing information protocol that has as metric the hop count. The other kind of protocols that we have are the link state protocols. Link state protocols are, in this case, the routing is performed by every switch in the network. The basic concept of link state protocols is that every node, every switch constructs a map of the network, and based on this map of the network, basically using the Dijkstra protocol define a route for the other routers or the other switches in the case of software-defined networking in the network. What are the most important witnesses related to the link state protocols? As we need to store information about this map that every node builds, as we need to construct the routes to all the other routers in the autonomous system. We need more memory, more processing power, and on the other side, we need to understand its operation in a deeper way. Basically, it's so important, for example, when we need to define the use of the open shortest path first, OSP in a network is very difficult, and it's important to highlight that the OSPF protocol used as weight cost in the calculation of the paths, a very simple formula that define a reference bandwidth divided by the current or the actual interface bandwidth available in the network. And the calculation of the paths is performed by using Distra with this weight cost. Okay. Finally, here we have different problems with the distant vector protocols, with the link state protocols, but the most important problem that I want to highlight is that this kind of protocols doesn't learn from past decisions. Okay, then RIP, OSPF, it doesn't learn from past decisions. Then if these protocols are taking decisions that lead to congestion, they can repeat that decision because they don't learn from past decisions. That's the main problem, okay? And this problem is very important, mainly in data center networks, okay? Then in data center networks, in very large networks, it's so important to learn from past decisions to avoid congestion. Okay, in this figure, we can see a scenario, a very simple scenario, in order to illustrate what is the problem that we want to address with reinforcement learning. Then let's consider a simple network consisting of 9 routers. The routing strategy on each router will show a route from several alternative paths to connect each source destination in the network. In this network, router 1, 2, and 3 receive incoming packets and send them to destination router, that is the router 9. Before the emergence of burst traffic, the load on router 6 is small, so the traditional routing protocol usually chooses this router to forward packets to the destination, to the router 9. Okay, but what happens if we assume that the traffic patterns generated by router 1, 2, and 3 have a behavior similar to the show in the figure that present different bursts and different types. Then, when these bursts occur in the network, the router seat is going to be congested. But the problem here is the traditional routers and traditional protocols like RIP, OSPF, and does learn from past decisions. Then they are going to send the traffic by using the router 6. But in this case, this router is going to be congested. Then this is the problem that we want to address in this in this presentation. And the idea is how to address by using reinforcement learning. Okay. Then, in summary, traditional routing protocols like OSPF, RIP employ limited information to make routing decisions. This limited information is associated that this information is not considering, for instance, different key performance indicators related to quality of service. Then, this use of limited information to make routing decisions can lead to a slow adaptation to traffic variability. And during or in the network models, in the modern networks, we need to adapt quickly to the traffic variability. Okay. Okay. Then here in after, I'm going to discuss how to propose an intelligent routing based on reinforcement learning, specifically for software-defined networking. Okay. Then before presenting the approach, I'm going to discuss, okay, what is reinforcement learning, what is software-defined networking, and what is the main idea of using reinforcement learning for solving this kind of problem. Okay. Sorry. Okay. Entonces, then this slide presents a traditional network in which the routing function is distributed and performed in a monolithic way by using highly tightened control and forwarding planes. Then, in this case, we have routers. These routers, every router is performing the routing process and the forwarding process. Okay, and this is a traditional network. Then, okay, the idea with software-defined networking is that the control of the network be centralized. Okay, in this case, this centralization is logically. Okay, this means that we can have different quantity of service running the network operating system. In practice, this network operating system is called like a SDN controller. Okay, and this SDN controller can be run as a set of or a cluster of service running this functionality. Okay, and the other idea of in the software-defined network is to the specific features like firewall, load balancing, NAT, DHCP, or new routing applications can run on the top of the network operating system, on the top of the controller. Okay, and this is the basically idea of the software-defined networking. Okay, to say a formal definition, SDN is an emerging architecture that is dynamic, manageable, cost-effective, and adaptable, and this is ideal for the high bandwidth dynamic nature of today's application. And this architecture decouples the network control and forwarding functions, like we can see in this slide. Okay. Okay. In this figure, we can see the SDN architecture. This SDN architecture is the classical architecture defined by the ONF. The ONF is the organization that defines the different standards related to SDN. In this case, we have a forwarding plane. The forwarding plane in SDN moves the data packets on the physical network layer to their destination. In this case, in SDN, we have a forwarding plane that is only in charge of moving packets, okay? Because the intelligence on the network is translated to the control plane. In this case, then, in the control plane is responsible for providing the intelligence behind the data transportation. It establishes and defines the neighborhood topology of the network, accumulates information, and the control plane permits to adapt to the change in the network as they happen, okay? And the controller offers its functionalities like the state of the network to the application plane, or another authors call this like service plane. And in this service plane, we can perform functionalities related to load balancing, firewall, and others. And some authors locate in the application plane the management functions like orchestration, configuration, and so on. Okay. Okay. Then this work, the idea of using reinforcement learning in the context of software-defined networking is related to the use of a knowledge plane. Okay. Then, in order to create this, the solution that I'm going to present in this paper, we use the concept of knowledge plane. But the idea to consider a knowledge plane for networking was proposed in 2003 by David Clark from the MIT. And this concept was revisited in 2017 by Mestres and others. And this concept is to introduce a knowledge plane to the network. Okay, then we can see in the figure that we have the data plane, the control plane, and in this case, the control plane is including the service plane that we see in the last slide. And on the top of that control plane, we have a knowledge plane, okay? And the idea in this knowledge plane is to run machine learning techniques, okay? And in this proposal of knowledge-defined networking, that is the idea to use a managed plane horizontal to the other planes, control plane and data plane. Then is a redefinition of the software-defined architecture in order to obtain a knowledge-defined architecture. Okay, then basically we use the knowledge-defined architecture to present a solution for routing in the context of defined network. Okay, then okay, what is the idea? Then the idea is to include in this knowledge plane reinforcement learning. Okay, briefly, reinforcement learning models are defined based on states and actions, okay, and their corresponding rewards. Then the idea is that the system based on reinforcement learning find the best actions to maximize accumulate reward by interacting with the environment. Then the agent executes an action when on the environment, the agent, the state, and it's going to provide also a reward related with that state. And by using this information, the agent is going to calculate, for instance, a Q table in which is going to store the information related, this action and this state obtains this reward. And the idea is to maximize or select the action that obtains the highest value of in the Q value. Okay, that's like a simple explanation of reinforcement learning. Okay, then specifically, I'm going to talk about the Q-learning technique. Q-learning is a model-free technique. It's a reinforcement learning technique that is model-free. This means that Q-learning does not need knowledge about the underlying reward resulting from taking a specific action in a particular state. Here, the Q-learning agent approximates the optimal action value. Okay, the optimal action value is the Q value. This Q value is stored in a Q table, like you can see in the slide. The idea is the agent visit all pair of actions state, and this action that the agent can execute is going to conduce the environment to this state, and the environment is going to get this reward, and this information is stored in this Q table. And the main idea is to select the action that maximize the reward. Okay. Okay, then considering this, okay, the concept of software-defined networking, the concept of knowledge-defined networking, the concept of reinforcement learning, okay, then we propose a solution that is called RSIR. Okay, this solution was published in a transactions journal recently. Okay, and in this case we have then you can see the management plane. Okay, you can see the knowledge plane, and you can see the control plane and the data plane. Okay, and in the knowledge plane we are going to locate our RS-based routing mechanism. Okay, that's okay. Then the idea here is to learn from past routing decisions. The element that is going to allow to learn from past decisions is the RL agent. Okay, then this architecture combines reinforcement learning, SDN, following the knowledge-defined networking paradigm in order to obtain the best routes by learning from past decisions. Okay, and the other important point here is that SDN has a centralized functioning. Our solution is not distributed. Our solution is centralized. Okay, but highlighting that centralized in a logical way. Okay, then RSIR use reinforcement learning to find the best route for all the source destination pairs by employing just 3 link state metrics: available bandwidth, loss, and delay. This is the 3 metrics that we are using in order to obtain the best routes. Okay, this is another important feature that our solution, because like you see in the previous slides, RIP only use the as metric the hop count, and OSPF only use bandwidth information. Okay, and in our case, we can provide routes with a trade-off between available bandwidth, loss, and delay. Then we have into account information related to the current and future network behavior. Okay, okay, that's all. Okay, then from a high-level point of view, RSIR operates as this figure shows. Okay, then what is the idea? First, the control plane collects network statistics. Okay, then the idea is to use a southbound interface. A southbound interface permits the communication between the control plane and the data plane and collect network information. Okay, this collection of the network information then is passed to the management plane. The management plane uses this information in order to calculate the link state information. In this case, the link state information is the bandwidth available, the latency, and the loss in the network. Okay, this information then is processed and is calculated by the management plane, and the management plane stores this information and sends this information and the required information to the agent that is located in the knowledge plane. This agent then is going to obtain the best route by using the Q-learning algorithm. In another slide, I'm going to explain in detail the algorithm. Okay, then by using the Q-learning algorithm, the agent calculate the best route for all pair of nodes in the data plane, and this information is communicated and sent to the control plane, and the control plane finally is going to install the flow in the switches. Okay, that's the main idea. Then we have 6 steps in order to obtain the statistics, process the statistics in order to get the link state information related to bandwidth, latency, loss, and after that we apply the Q-learning algorithm in order to get the best routes, and finally these best routes are used by the control plane, and the control plane install these routes in the data forwarding plane. Okay, that's the main idea. Okay, but here is my idea is not present my solution. My idea is, okay, how we can build a reinforcement learning solution. Then in order to create a Q-learning agent or reinforcement learning agent, and then, okay, how to model this? Okay, then from my experience, you need to define these 6 steps. First, you need to define the reward function. You need to define the space state, the action state, the optimal policy, the exploration and exploitation method, and finally, you need to build the routing algorithm based on, for instance, Q-learning, but you can use SARSA, or you can use another reinforcement learning method, or another deep reinforcement learning method. Okay, because these steps also operate for deep reinforcement learning. In this talk, I'm not going to talk about deep reinforcement learning but we have this solution also deployed by using the reinforcement learning. But the steps that we follow to create the solution basically are the same. Okay, then we need to, okay, this is so related with this part. Okay, then what we need, define the action space. We need to define the state space. We need to define the reward. We need to define the algorithm, and we need to define the optimal policy. Okay, that's the elements that I'm mentioning in this slide. Okay. 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 Then here we have, okay, we need to define what is the reward function. Then we are going to how to qualify the execution of an action. Then in this case, our reward function is related to 3 performance metrics: the loss in the links, the delay in the links, and the bandwidth available in the links. Okay, in this case, we define then that we want to minimize the reward. Okay, because we want to use link, we want to use routes with less loss, less latency, and with the highest bandwidth available. Okay, then we define this reward function. Then when the agent selects routes meeting this idea, this policy that use routes with few link, few delay, and high bandwidth available, then the reward that this decision is going to receive is high, is minimum. Okay, because we need minimize the reward. In this case, like obviously loss operates, loss, delay, and bandwidth operate with different magnitudes. We need to perform a normalization of this equation. Okay, then the equation 2 is the version of the reward in a formalized way, and the technique that we use to normalize this equation is presented in the equation 3. That is the is a technique known as maximization minimization. Okay. Okay, the second step is then define the state space. Okay, then the state space in this case corresponds to a switch on the data plane and a transition from one state to another state. Okay, and this translation obviously corresponds to a link connecting two switches. Okay, in this case, I'm going to talk about switches because in the SDN terminology, we don't talk about routers, we talk about switches. Okay, and then we need to define the state space, and the state space then is corresponds to a switch on the data plane and a transition from one state to another one. Okay, and in this case, the topology of the state space is a graph corresponding to the topology of the switches on the data plane. Okay, and in this case, the cardinality of the set of states is the number of switches on the data plane. Then the state space is in our proposal is going to grow according to the number of switches in the network. This means that if we have a large network, we have a large state space, okay? And specifically, we have a topology discovery module that is responsible for builds a topology map with nodes corresponding to the states in the state space. Okay, the other state then is define the action space. Okay, what are the actions that the agent can execute? Okay, in this case, this action is basically we are located in a node. Then the actions that that this switch can execute is moved to the neighbors. Okay, basically then our action space for each switch corresponds to the neighbors of that switch. Okay. Just give me a second. Okay. After that, just give me a second. Okay. After that, we need to define, okay, what is the optimal policy? Okay. And to define what is the optimal policy, we use Q-learning, and the idea is to minimize the reward value in the Q-learning routing process. Then the idea is that the RL agent learns to avoid links with a high delay, loss ratio, as well as prioritizing links with large available bandwidth. Okay, then that's the main differentiation with the RIP and OSPF. Okay, we are going to learn to avoid links with these characteristics. Okay, and in this case, the agent use the equation 4 that is presented in this slide to calculate the different Q values for each action for each switch in the network. Okay, then we are going to fill out this Q table by using this equation. That's basically the way in we obtain the optimal policy. Okay. Okay. In this equation, it's important to highlight two aspects. Okay. We have alpha. Alpha is a factor that indicates how the agent learns. Okay. For instance, if alpha is equal to 0, means the RL agent is unable to learn from the latest actions. Okay. While a factor with alpha equal to 1 means the agent to learn from the information, from the past information. Okay, and we can tune the value of alpha in order to define if we want to learn a lot from past decisions, or if we want to learn less from the past decision. Okay, this is a tuning process that usually is performed by testing the solution. Okay. Okay. Talking. Okay. The other step in the creation of the reinforcement learning solution is to define what is the exploration and exploitation method. Okay. The The exploration and exploitation method indicate if the RL agent is going to select a new or unknown previous selection, or always is going to select a past decision. Okay, in this case, basically the idea is the agent generates a random probability. This random probability is compared with a threshold. If this probability is less than that threshold, the agent is going to choose a random action, and if it's higher than this threshold, is going to select, in this case, the minimum Q value, because our optimal policy is oriented to select the minimum Q value, okay? But in other cases, maybe select to the maximum Q value. Depends like you model your solution, okay? And the last step is to define, okay, the reinforcement learning algorithm. In this case, we use Q-learning, but you can use SARSAR or another Q-learning approach, okay? Then we need, basically, this is the Q-learning algorithm, but in this case, the inputs are the learning rate that we need to define, that is the alpha. This is defined by testing, okay? The exploration and exploitation method, this is also defined by testing, okay? The number of learning episodes, in this case, the information that we are going to provide specifically is the network link state, okay? The network link state, and after that, we initialize the Q table in 0. Okay, all the information, all values of the Q learning are in 0. Are the lines 3 and 10 are going to fill the Q learning, and in the line 12 we are going to decide, okay, what is our best Q value in order to select the best path. In this case, the best Q value is the Q value with the minimum value, okay? Another important feature of our routing solution is our solution is proactive. This means that our solution is learning from the decisions, and in SDN, the paths are defined when a packet in happen in the network. But in our solution, the paths that cause the traffic in the network are calculated before the packet in happens, okay? Because decisions are taken by considering the network status, okay? The network status related to the link state information of the 3 indicators: available bandwidth, delay, and loss, okay? Then in this figure we can see in more detail, okay, then the control plane get information. This information is stored in a statistics module. This statistics module pass this information to the management plane. The management plane has a data processing module. This data processing module calculates link state information. This link state information is stored in a network information data repository. This data repository is used by the RL agent in order to obtain the information of the link state and the reward, and the RL-based agent explore and learns best routes by following the information that we define: the state space, action space, optimal policy, the algorithm, and so on. And these best routes are stored in the routes data repository, and the control plane, specifically the flow installation module, obtain that information and perform an installation process in every switch of the network. Okay, that's the process that finally we perform in the network. Okay, then, okay, my time is short. Okay, okay, from theory to practice. Okay, then how to conduce how to lead this to the practice. Then to perform this in a practical way, we implement the control plane by using the RU controller. Then this means that the statistics, topology, discovery, and flow installation process basically was developed by using a Python library that provides this controller. And the knowledge plane, specifically the reinforcement learning agent, was built by using Python and the Panda, specifically the Pandas library. And the management plane also use Python and the Pandas library in order to processing and generating all the information related to the link state metrics. Okay, and the data plane was implemented by using open base switches. Okay, that's that we use in order to generate a prototype of our solution and go from the theory to practice. Okay. Then another important point here is that we use a topology of a real network. Okay, specifically we use the topology of the GEAN network. The GEAN network is an academic research network in Europe. Okay, and we use this topology. Then the topology that you can see in this figure and the information of the link capacities and so on is from a real network. Okay, it's not a information of a network that we build in order to test. Is a real network. In addition, the information that the network traffic that we use in order to test our routing solution are real network traces. Okay, then we use real network topology and we use real network traffic in order to test our routing solution. Okay, because our idea finally was to compare our solution with RIP and OSPF. Okay. Okay. Okay, I want to finish. Okay, in time, but okay. Then here in these figures, obviously, after implement the prototype, build the test environment, we evaluate the solution by using different metrics. The first metric was the stretch. What is the stretch? The stretch measure the length of the paths. Okay. Then in this figure we can see RSIR. Our solution is in blue. Then our solution is using the paths, the shorter paths than the other the other solution in average. Okay, then in this case we can see RSIR outperforms in terms of stretch to the different Distra solutions. Okay, why we use or why we compare with Distra? Because OSPF, that is the solution used in autonomous systems in the real life, is use the Distra algorithm. Okay, then we compare with Distra. Obviously, this non-Distra distributed, because we want to perform a fair comparison. Okay, then a fair comparison. Then we perform Distra in the controller. Then these solutions are Distra executing on the top of the controller. Okay, it's important to clarify that because RSIR is also running in a centralized way. Then we can see that RSIR outperforms, obtains a best stretch than Distra delay, than Distra loss, and Distra composite. Distra composite is a Distra that use as weights codes in order to calculate the best routes, delay, loss, and bandwidth. Okay, is the combination of these metrics. And okay, but in this case, RSIR obtains an stretch a little higher, 3% higher than Distra based on bandwidth. Okay. In terms of delay, okay, what happened around the delay of the network? Okay, in this case, RSIR has a best behavior that Distra composite, Distra delay, Distra loss, and Distra bandwidth. Okay, this means that RSIR use the shortest path less congested, okay, in order to obtain less delay. That's the meaning of this result. Okay, and the other important point is that again, RSIR obtains routes that generates less loss than the other solutions. Okay, this means, okay, again, the shortest paths that lead to get less delay and less loss. Okay, and finally, the throughput that we obtain in the links is less. Why? Because we are distributing the traffic in the network, okay, in a broad way. This means that this distribution of the traffic in the network is conducting to obtain less delay and less loss. Okay. Okay, it's in time. Then, in order to conclude the presentation, finally we perform another evaluation, and we compare basically with OSPF and RIP. And RIP typically take 30 seconds to handle a topological change, okay, in the test. OSPF reacts approximately in 9 seconds, and our solution takes on average almost 10 seconds to handle a change. Okay, but we are going to have a topology. We are handling topological changes 1 second slow than OSPF, but our routes are better in terms of delay, loss, and throughput. Okay, that's the conclusion. Okay, but okay, what is the open challenges are here? First, the convergence time takes in real networks use multiple SDN controllers, and okay, really we evaluate this solution to use a deep reinforcement learning agent, but to present a deep reinforcement learning is necessary first to know like reinforcement learning work. Because of that, in this presentation, I have focused more in reinforcement learning than in this reinforcement learning. Then here is the figure that our solution, but in this case, using deep reinforcement learning with two neural networks with multiple hidden layers and so on, that improves the results of the RSIR. Then we have an RSIR++, and that RSIR++ improve the results the good results that we obtain with RSIR classical. Finally, I want to perform some acknowledgements for my PhD student, Daniela Casas. She is performing his PhD studies in the University of Campinas, Brazil, and the Professor Nelson Fonseca, that he works in collaboration with me in these works related to reinforcement learning, deep reinforcement learning, and he is a senior member from IEEE. If you want to explore this solution, okay, the solution, the full explanation of the solution you can find in this URL. You can download the paper, and in the GitHub you can download all the scripts that we developed in order to implement our solution. Okay. Thank you very much for listening me. Okay.
Thank you.
Hey everyone. So if you have any questions, feel free to ask. You can even drop the questions in the chat box.
Excuse me, sir. Ram Prakash here. One question I'd like to ask is, does this change in the way, like this addition that you have to the network, like a normal network in a data center, so you have these new modules that do all the computation, does it have any effect on power consumption? Because if we are talking about large scale data centers and all, how will it impact power consumption?
Okay, that's a great question. Okay, our solution doesn't need any modification on the switches. Then the switches don't have problems related to energy consumption. Okay. But okay, during the develop, our first idea was to locate the knowledge plane inside the controller plane. Okay, but we note the controller doesn't operate correctly when the network grow. Then because obviously here I have presenting just one test in one network, but we test in large networks. Okay, then we need to separate the knowledge plane from the control plane to get best results. But the good news here is that the knowledge plane operates can operate in a blade in the data center. Okay, and we don't perform tests in energy consumption related to this knowledge plane. Okay, but we evaluate the computational complexity, and this computational complexity is very similar to the computational complexity of the OSPF. Then we expect, without performing tests right now, that the energy consumption is not so high. Okay, but it's necessary yet to perform these tests. Okay.
Okay, sir. Thank you. There are also a few questions in the chat. Adeep asks, how effective is this technique in places where network facilities are poor?
Can you repeat me, please?
So he asks, how effective will this technique be if network strength is poor? I think that's what he means. In general, the architecture, the hardware, if the facilities aren't that great.
Okay. Basically, we are going. We need to add that knowledge plane, and the main idea behind the architecture that we define is not touch the control plane and don't touch the forwarding plane. Okay, but another solution that recently are presenting are based on P4 or the data plane programmability, but this means that you need hardware supporting P4 and supporting that kind of programmability. But our solution don't touch the data plane and don't touch the controller plane finally. Then from an architectural point of view, our solution is just to add another plugin that communicates with the control plane, and the solution is going to operate that.
All right. There's another question in the chat. Muktesh asks, what further breakthroughs can we expect in this field?
What
further breakthroughs can we expect in this field?
What I don't understand.
Any more advancements, improvements on this?
Okay. Okay. The final idea is to propose a solution that can replace OSPF and RIP in autonomous systems based on software-defined networking. Okay, that's the final idea that we want to develop. Then, in order to achieve that, we need to improve the time that we spend to calculate the routes. Okay, for instance, OSPF spent around 5 seconds to calculate the routes in the different tests that we perform. Okay, and our solution based on reinforcement learning, okay, using limited resources in the test, spend around 7 seconds. Then we need to improve, we need to tune the solution in order to achieve a similar time to SPF, or decrease or obtain a lower time that OSPF. Okay, that's a very great challenge. Okay, because obviously OSPF is a well-known protocol, and is used in practically all networks in the real life. Okay.
All right. Do we have any more questions?
Okay, señores.
All right then. So I would like to hand it over to Meghna for the vote of thanks.
So, good evening, everyone. I'm Meghana M. Shastri, the Secretary of Women in Engineering NISP, and I'm delighted to deliver the vote of thanks on this wonderful day. On behalf of NISP and on my own behalf, I'd like to thank Professor Oscar M Caicedo for conducting this amazing session on the topic of deep reinforcement learning for networking. The webinar session was full of knowledge and gave deep insights into the topic. All the concepts, maybe network learning problem or software defined networking or the reinforcement learning, which Professor Oscar taught us, were extremely informative. I'm sure everyone has benefited a lot and learned quite a lot today. Next, I'd like to thank all the participants for being such a good audience. We at NISB will be conducting many such events and we hope you all to be a part of them. Thank you again and have a nice day.
See you.
Sir.
Thank you for the invitation.
Thank you, sir. Thank you for attending. And participants, thank you all. Your certificates will be mailed to you. And especially, I'd like to thank Professor Oscar, sir, who's taken his valuable time to conduct this session for us at NIIEEE Student Branch. Thank you, sir. Have a great day.
Have a great day for everyone. Bye-bye.
Bye, sir. Thank you.
Thank you, sir.